diagrams and set operation. The following are the objectives for today's lesson. First, you would gain understanding of the meaning of a universal set after the discussion of today's section. And then understand the basic ideas of a Venn diagram. Use Venn diagrams to visualize relationships between two sets. Also find the complement of a set, the intersection of two sets, and find the union of two sets. Now let's define universal set. The universal set is a general set that contains all the elements under discussion. This figure here is what we call a Venn diagram. Now this bigger set here, this general set here, is the universal set. The person who created the Venn diagram is John Venn. Venn diagrams are used to show visual representations or relationships among sets. Now, usually, the universal set is represented by a rectangle, and it contains all the elements under consideration. Subsets within the universal set are represented or depicted by circles or other shapes. Now, for example, let's use the given Venn diagram here to determine the following sets. Now, usually we denote U as our universal set. Again, the universal set is the general set that contains all the elements under discussion. Now, in the figure here, U is for the universal set, and then this is set A. Now, set A is the set containing the square and triangle. And then outside of set A are the elements $, M, and 5. So therefore, the universal set is the set of all elements in this set here, like the square, the triangle, the $, M, and 5. That's the universal set. Set A contains this square here and the triangle. The set of elements in U that are not in A, meaning the set of all elements in the universal set, but outside of this set here. This is set A, not in A. Those are actually these elements here. So the set containing the $, M, and 5. Let's consider this Venn diagram here that has two sets, A and B. Now in this figure here, we are given two sets. The two sets A and B here have no elements in common. They actually do not overlap. So we call this the disjoint sets. So disjoint sets are two sets that have no elements in common. And their Venn diagram is this figure here. Proper subsets can be represented by this using Venn diagram. As you recall, for proper subsets, these are sets wherein all the elements of the proper subsets are also elements of the bigger set. So if A is a proper subset of B, everything in A can be found in B. So this is how you would represent a proper subset. So as you can see, all the elements in A here are also inside set B. In our previous discussion, we know equal sets are sets to have exactly the same elements. So therefore, if two sets A and B are said to be equal, then A is a subset of B and B is a subset of A. And using the Venn diagram representation, this is how you would represent sets A and B to be equal. As you see, they're just overlapped. Now, for sets with some common elements, that means we are actually referring to this region here. The elements of this set here are common to both A and B, meaning those elements can be found in A at the same time in B. So if set A and set B have at least one element in common, then the circles representing the sets must overlap. So this is the Venn diagram representation of a set with common elements. Let's consider this example here. Use this Venn diagram to determine the universal set, set B, and the set of elements in A but not in B. Now notice that set A here overlaps with set B. For letter A, universal set contains all the elements under consideration. So these would be the elements in this region plus the elements in this region, and then the elements in this region, and then the elements in this region. So we will just have to list everything down. This will be A, B, C, and then D, E, F, G. So these numbers here, these Roman numeral numbers here, are just used to denote the number of the region. So for I region, you have A, B, and C. So that's how you got that, A, B, and C. And then D, for that region, you have element D, and then E, and then F and G. So therefore, with that, set B contains region 2 and 3. So that contains elements D and E. The set of elements in A, so it should be in A, but not in B. We're referring to this region here, only on this region. So we're referring to region I. That is in A, but should not be in B. And the elements in A that are in B is in region 2. So therefore, the set of elements in A, not in B, is region 1, and that is the set containing A, B, and C. Now, what about the elements in the universal set that are not in B? So we are actually referring to the region outside of B. Outside of B are regions 1 and 4. That is outside of B. If you look at that one, it is actually this region here. The elements that you can find outside of B are A, B, C, and F, G. Now, the set of elements in both A and B. So what are the set of elements that are in both A and B? In both A and B are the intersection of A and B. The intersection of A and B is this region here, region 2. So that is the set containing D. Now let us define the complement of a set. The complement of set A, symbolized by A prime, is the set of all elements in the universal set that are not in A. This idea can be expressed in a set builder notation as follows. So A complement, or the complement of A, is the set of all elements in the universal set but are not in A. So using the Venn diagram representation, we are actually referring to the region outside of A. So this blue region here, the shaded region that lies outside of the circle, is A prime, or the complement of A. Now let's consider the following examples. So given this universal set here, which is the set containing 1, 2, 3, 4, 5, 6, 7, 8, 9, and set A to be the set containing 1, 3, 4, 7, we want to find the complement of A. So the complement of A are the elements outside of this circle A here. And the elements are 2, 5, 6, 8, and 9. Then let's define the intersection of sets. The intersection of sets A and B, written by this symbol here, so this can be read as A intersection B. So the intersection of A and B is the set of elements common to both set A and set B. So these are the elements that are in the intersection. So if you remember that in the Venn diagram notation, so the intersection of the two sets, the elements there are common to both sets, both set A and set B. Now this definition can be expressed using a set builder notation as follows. So A intersection B is a set of all x such that x is an element in A and x is an element of B. Now using the definition of the intersection of two sets, we want to find the following intersections. So for letter A, we're given this set and this set. We want to find the intersection. Again, when you say intersection, it is elements common to both sets. So you just have to compare the elements here. Is 7 found in here? No. But 8 is here on this set and also in this set. So therefore 8 is in the intersection. Also 9, no, it's not common. 10 is common. 10 is an element on the first set, an element also on the second set. 11 and 12 are not. So therefore, the intersection is the set containing 8 and 10. These two numbers here, 8 and 10, are common to both sets here, this set and this set. Now for letter B, we do the same thing. We compare the elements and see what elements are common to both. Do you see any elements that can be found here and also in here? And fortunately, there are no elements that belongs to the first set and also to the second set. So therefore, the intersection of the two sets here is empty. So if the two sets have no intersection at all, we've learned that those two sets are called disjoint sets. Now, if we want to get an intersection of this set and the empty set, this one contains nothing. So what's the intersection? It's just the empty set. Let's discuss the union of sets. The union of set A and set B is written using this symbol here. This is used to denote union. And this pertains to the set of elements that are members of set A or of set B or of both sets. Meaning to say you are just going to get all the elements on all sets. You just have to gather all elements of both sets. So when you say union, you're just going to join the sets. This is how we're going to define the union of two sets. A union B is the set of all x such that x is either in A or in B. To understand the definition of the union of two sets, we consider the following examples. Find each of the following unions. So given this set here and this set here, we want to find the union. When you say union, you just want to gather all distinct elements. Since 8 is not distinct, you have 8 here and 8 here, you're just going to write that one once. And also for 10. 10 here will only be written once. So therefore, the union is the set of all elements containing 6, 7, 8, 9, 10, 11, and 12. Next, for these two sets here, find the union. Meaning you're just going to write down all the elements and then list all those elements that appeared twice. You just have to list them once. The union of these two sets here is the set containing 1, 2, 3, 4, 5, 6, 7, 8, and 9. Lastly, for these two sets here, the union of these two sets is the set containing 1, 3, 5, 7, and 9. Because this empty set here contains nothing. It does not contain anything. So don't get confused. This one does not contain 0. When you say empty, it's nothing. Nothing is in there. Now with that, it is important to take note that the intersection of the set A and the empty set is just empty. And the union of set A and the empty set is just set A, because empty set contains nothing. Okay, so if you are going to combine them, then there's nothing to be added to set A. Therefore, the union is just A. And here, the intersection, the common to both is nothing, because there's nothing in here.